All right, are there any questions from last time? So last time we were trying to address the problem of classifier design, right? And so here you have a class label y, right? And you basically have a feature vector x, which is d-dimensional, right? So looking at the feature vector x, right, you want to make a prediction for the class label, right? So that is the classification problem, right? So classification involves the feature vector x, which is d-dimensional, that is composed of random variables of features. Then you have a binary random variable y, because we are assuming that there are two classes, 0 and 1, right? And the classifier is basically a function that is going to take the feature vector as its input and spit out a class label, either 0 or 1, right? The error epsilon sub psi of that classifier is the probability of misclassification, right? Is the probability of making a wrong classification, right? And I showed you last time that that equals the expected mean absolute difference, expected value of the absolute value of y minus psi x, right? I explained to you last time why that is the case. And because this is binary classification, this is also this quantity is also equal to the mean square error, right? Now we want to find out the best possible classifier, right? So the optimal classifier psi sub d, that means the optimal classifier on d-dimensional feature space, is the one which has got the minimal error, again denoted by epsilon sub d, among all binary functions on d-dimensional space, so that it is the minimal mean absolute error predictor of y, right? So psi d, that best classifier or the optimal classifier, is called the Bayes classifier, right? The classifier that has the minimum error, right? And the error of that Bayes classifier is called the Bayes error, right? Now classification accuracy, and thus the error, will depend on the probability distribution of the feature label pair xy, right? Like if y is independent of x, then you're not going to get any information, right? So looking at x is not going to allow you to do good classification, right? So the feature label distribution is going to decide the accuracy of the classification. Now let's just introduce some, or let's just define a few quantities here that will be necessary to derive the expression for the optimal classifier, right? So the posterior distribution for x, see, x is the observation, that's the feature that you're going to see. So the posterior distribution for x is defined by eta x equals the joint density of x and y, right? Evaluated at y equal to 1, divided by the marginal density of x, right? So eta x actually gives you the probability that y equal to 1 given x equal to x. Because see, here you're dividing the probability or the density, right, at x and at 1, right, divided by the density of x, right? So from the definition of conditional probability, right, this quantity is going to be the probability that y is going to be 1, the class label is going to be 1 given the observation capital X equal to x, right? And in this binary setting, eta x is also the conditional expectation of y given x, right? And I explained that to you last time, why that is the case, right? Because there are two possible values for y. They are 0 and 1. So if you are calculating the conditional expectation, it's going to be 0 times the probability that y equal to 0 given x plus 1 times the probability y equal to 1 given x, right? So the only term that survives is eta of x. Agree? Any questions so far? So now if you're looking at an arbitrary classifier psi, right? Remember the classifier is a design function on d-dimensional feature space, right? So the error of that classifier, if you want to compute that, right, that is going to be made up of two parts, right? See, here you have eta of x multiplied by fx x. Okay, what is this quantity? Again, eta of x, we said, is that the probability of y equal to 1 conditioned on x, all right? If you multiply that by the probability of x, what do you get? What? No, you get the probability of y equal to 1 and x, right? And here it's, so that's the quantity that you get here. Okay, so this is the probability that y equal to 1, all right, conditioned on x. Okay, if that is going to constitute an error, all right, if that is going to constitute erroneous classification, all right, if probability if you're looking at remember the classification error is the probability of misclassification, right? So I want the integral over here to capture that probability, right? That means I must look. So that means for a value of x, uh, that is captured by this integral, all right? If psi of x, if the classifier spits out a class label 0, right, for that corresponding x, right, then this is the probability of misclassification, because this is the probability that y equal to 1 conditioned on x. Right, agree? So if I integrate this, right, over all x such that the class label is 0, right, the class label that the classifier is spitting out is 0, then this basically gives you one type of error, right, where really the probability that y equal to 1 condition on x is different from 0, right, and I am actually spitting out a class label of 0, right. This integral is just the opposite, right. Here I had eta of x, here I have 1 minus eta of x. 1 minus eta of x is going to be the probability that the class label is 0 given x, right, multiplied by fx of x, that's going to give you the joint density, right, class label equal to 0 and x, right. So in this case I'm making a mistake, right, if I spit out a class label of 1, right. So that's why this is over the set of all x such that psi x equals 1, right, dx. And then you combine these two errors together, that is the total probability, because you've looked at the two possibilities, right, that's the total probability of misclassification, right. Right. So now I want to choose these guys, all right? I want to choose this psi, all right, this function here, classifier here, and the classifier here, to minimize this fellow, okay? Now look, eta of x, all right, we said was that was the probability that y equal to 1 conditioned on x, right? So that is a number between 0 and 1, right? So here you got eta of x, right? Here you have 1 minus eta of x, right? This fx of x is common between this integral and the other integral, right? So really, I mean, whether you choose one integral or the other, that will depend on the value of eta of x. If eta of x is less than 1/2, right, I'm better off if for those values of x, this integral is picked up. Because in that case, eta of x is going to be less than 1 minus eta of x. If eta of x is greater than 1/2, I would like those cases to be picked up in the second integral. Right? So how should I choose this optimal classifier? So psi d of x, all right, should be chosen as 0 if eta of x is less than or equal to 1/2, right? Because if I choose psi d of x equal to 0, then those x's are being picked up in the first integral, right? And eta of x is less than or equal to 1/2, which means that 1 minus eta of x is actually greater than or equal to 1/2, so I'm picking up the smaller one. Right? So that's how I come up with the optimal classifier. So psi d of x is going to be 0 if the probability that y equal to 1 conditioned on x is less than or equal to 1/2, right? And is 1 if probability that y equal to 1 conditioned on x is greater than 1/2, right? And this is the base classifier, right? So psi d of x is defined to be 0. So you're assigning the class label 0 or 1 according to whether y is less or more likely to be 1 given x, right? And this makes intuitive sense. Right? I mean, you're seeing x, all right? Which one is more likely? All right, y equal to 0 or y equal to 1? So is that clear? So this is the derivation of the base classifier, right? And now I'm just going to plug in this classifier. Oh, in here, I will have the base error, right? Because this one is telling me that I have to choose psi dx equal to 0, all right, if eta of x is less than or equal to 1/2, all right? So I'm going to say psi x equal to 0. So this is going to be over all x's such that eta of x is less than or equal to 1/2, right? I will sum this portion, right? And here is going to be all x's such that eta of x is greater than 1/2, right? That will be the expression for the error of the base classifier. Is that clear to everybody? Right? So this is Bayesian classification, right? So it follows from the above two equations that the base error is given by epsilon d equals the set of all x where eta x is less than or equal to 1/2, because for all these x's you're going to spit out psi x equal to 0, right? And then here is going to be all x such that eta x greater than 1/2, right? So in theory we have solved the classification problem, right? We've defined the probability of misclassification, right? And then looking at that expression, we have basically picked up the classifier, and we have the error of the optimal or the best classifier. The problem with the base classifier is that we typically do not know the class conditional probabilities, because you need to know eta of x, right? Probability of y equal to 1 given x, probability of y equal to 0 given x. These are not given to you, right? You have to learn those from the sample. So if it's a textbook problem, those will be given to you. And you can just apply whatever we covered here. And in fact, you'll do some homework problems where you're going to do that, right? But in the real world, you're going to have to learn that stuff, right? So an obvious approach would be to estimate these conditional probabilities from the data. But often you don't have sufficient data to obtain good estimates of eta of x, right? So moreover, good classifiers can be obtained even when we lack sufficient data for satisfactory density estimation. So even in cases where you cannot estimate eta of x, there are ways, at which you can arrive at reasonably good classifiers. All right, any questions on this? So this is the Bayes classifier, and I also introduced the Bayes error. So now, because those probabilities that you need for designing the Bayes classifier, they're not given to you, right? You have to do classifier design, you have to estimate them, right? So you will take samples, right? You will take samples of feature label pairs, right? Because X is there, and then you have the class label, right? So it's like looking at a lot of examples you will learn, right? That's the whole idea, right? That's how a human being learns too, right? You're given an example of this is the feature vector, this is the classification. Given a whole bunch of examples, hopefully if you're given a new example, you can do the correct classification. Right? So the design of a classifier psi n. So now the classifier that you're going to get, it depends on the sample n, right? A sample of size n. So psi n from a random sample Sn, which has got these feature label pairs. So you have the feature vector x1 with the corresponding class label y1. Feature vector x2 with the corresponding class label y2 and so on. Right? So you have n of these pairs, right? So of vector label pairs drawn from the feature label distribution requires a classification rule that is going to operate on random samples to yield a classifier. Right? The probability is not given to you, but now you're going to operate on random samples and find the classifier out. So a classification rule is a mapping psi n. Again, it depends on the sample n of size n, which takes this these n samples of feature vector label pairs, right? So you have a feature vector here, d-dimensional feature vector, class label, right? You have n of them, right? So n samples, and you're going to produce a rule where f is the family of 0, 1 valued functions on Rd, because you're going to spit out the class label, right? So this is going to be either a 0 or a 1, right? So now once you're given a sample, once that sample is fixed, then you obtain a design classifier. Okay. Before you have the sample, it's a classification rule that is going to operate on the sample. Once you stick in a sample, then you have the design classifier psi n, which is this boldface capital psi sub n operating on the sample Sn, right? Right? According to the rule psi n, according to the rule boldface psi n. So the Bayes error, okay, that is something that if you had the conditional, if you had those probabilities, you could calculate the Bayes error, like I showed you, right? How to calculate the Bayes error. But in reality, you cannot, right? So you're going to try to estimate that. So the Bayes error epsilon d is going to be estimated by the error epsilon sub n of this design classifier psi n, right? So there is a design cost, because in general, when you're learning from the data, you're not going to get epsilon d exactly, right? It's going to be something larger than epsilon d, right? So this is the design error, the design cost, right? And delta sub n is sample dependent. It's going to be a sample dependent random variable. And so if it's a random variable, okay, because there is a sample, so there's randomness, so you have to take the expectation if you're going to do any comparisons, right? The expected value of delta sub n, and the expectation being relative to all possible samples, right? So the expected error of the classifier psi n, the design classifier, you can decompose it into two parts. There will be the Bayes error, right, which is for the classifier that you haven't been able to design, plus the expected value of the design error. Okay. And the hope is that if the sample size becomes large, right, this fellow will go to 0, right? It will go to 0, and then the error of the design classifier will approach the Bayes error, right? That is true, but that's only if the sample size is large, right? If the sample size is small, then you are in trouble, right? And for the kind of problems that we are talking about here, the sample size will be small. Because if you're using microarray data, you might have like 10,000 genes, right? Maybe only 100 samples. You'll be lucky if you have 50 or 100 samples. Okay. So how do you get around that problem? And again, I'm giving you just a preview of what's coming, all right? So the Bayes classifier is the best classifier without any constraints, right? You're just, you have made no assumptions about the structure of the classifier, right? If instead of trying to do unconstrained classification, right? Right. In which case, to learn the classifier, I will need lot of data. I might want to go ahead and impose constraints on the classifier. Maybe I'll say it's going to be a linear classifier, right? It's going to be a straight line, right? Or a plane that is dividing two regions, right? Then in that case, things become a lot more manageable, right? Because as soon as you have a plane, if it's d-dimensional space, you just need d of those constants, and you can do the design. Okay, it'll require a lot less data. In the process, what have you done? You have given up optimality, because if you see, like, your optimal classifier, the base classifier, it may not be a linear classifier, right? So if you're doing a linear classifier, means you're not going to do as well as the base classifier, right? Assuming that all the probability densities were given to you, right? You're not going to do as well. But on the other hand, for small samples, right, you might be better off, because to learn the base classifier, you need a lot of data, right? But to learn the linear classifier, you might need a lot less data. And if you're operating in the small sample region, right, you're probably better off putting in that constraint. Okay, that's the whole idea. There'll be a lot of text and some figures and all that, but that's the idea. That's the big picture. Now here, this is some terminology. Again, there is a course on pattern recognition, right, that is given in this department every, I think, spring semester. I think it's 649. So they will do a lot of these details, right? I'm trying to give you the big picture, and I will introduce some simple classification rules. You'll do some homework, so you'll have some familiarity, right? But if you want to get into the details of how all these results are derived and all that, you have to probably take that course. And I'm not even sure that they cover all those things in that course, but I think that will equip you with the tools that are needed. Yeah, have you taken that course? Okay, okay. Yes, for the others, some people are thinking about what courses to take next semester. That's a course that you can look at, because what I'm covering, like maybe in 1 or 2 lectures, all right, they'll probably spend a lot more time. Okay. And more mathematically rigorous and all that. I'm trying to give the big picture, because I don't want you to get lost in the details here, right? I want you to pick up the biology, whether it is animal biology or plant biology. The rest of the stuff, mathematically, yeah, it can be complicated, but you're all double E's, I know you can do that, right? The biology is the handicap here, right? And that's what I'm trying to bridge in this course, right? And of course, give you some flavor about the engineering involved, right? So that way if you're taking that course, why are you doing that stuff, right? Okay, so asymptotic properties of a classification rule concern large samples as n goes to infinity. A rule is said to be consistent for a distribution of x, y, right? That means a joint distribution of the feature and the labels, all right? If delta n, right, that quantity, that design error that I defined, right, the delta n that I defined over here, right, if that goes to 0 in the mean, all right, which means that the expectation of delta n, because this is a random variable, that should go to 0 as n goes to infinity. So for a consistent rule, the expected design cost can be made arbitrarily small for a sufficiently large amount of data, right? Now, since rarely is there a good estimate of the distribution in pattern recognition, rules for which convergence is independent of the distribution are desirable, right? So if you have a classification rule where delta n goes to 0 regardless of the feature level distribution, feature label distribution, right, with the joint distribution of x and y, you will call those rules universally consistent, right? And universal consistency is going to be useful for large samples, but it'll be of little consequence for small samples, because when you have small samples, delta n is not going to go to 0, right? So it doesn't really help you much. Now, we are going to discuss a few well-known and well-studied classification rules, our intent being to use them to illustrate methodology and issues, right? We are not going to go into the details, into a detailed course on pattern recognition, right? So one of the rules that is there is called the nearest neighbor rule, right? So you have so let's say you have 2 different class labels, all right? So let's say some of those things are already labeled, let's say, okay? So you have, let's say, dots and squares, right? Spread out, let's say, over 2-dimensional space, all right? So if there is some point, right, some sample point that you want to classify, right, you're going to look at the nearest. What is the nearest neighbor, okay, for that particular point? And you could use Euclidean distance, all right? So is the nearest neighbor a circle or a cross? Okay, if it's a circle, then you will say that this point also has the label of a circle, right? That's all there is to it, right? That's the nearest neighbor rule. Then you have something that is called the k nearest neighbor rule, where k is an odd number, right? So instead of just using the the label, instead of just inheriting the label from the nearest neighbor, right, you take an odd number of neighbors, right, and you use the majority label from the neighbors, right. So let's say you have three, all right, you have three neighbors, all right. So let's say two of them are circles and one of them is a square. Then this one also you will assign a circle, right. So that's the k nearest neighbor rule, and obviously k has to be an odd number because you don't want any ties in there, okay. So 3, 5, and so on, all right. So that's so, and these are some expressions. I'm not going to worry about this because we are not covering theory about how to derive these. All right, you'll have to read papers and probably books to figure out what is involved. All right, and maybe in 649 they cover some of that.
They go, especially this one. You do a project with this one.
Yeah. So they do that. So if you have an appetite for that kind of stuff, by all means go for it. Right.
One thing about it that's really interesting is that if you use one, it tends to be more accurate, but you also can't necessarily be so certain of your results.
Yeah.
You are classifying only by the closest one, which may be an arbitrary error.
Yeah. Yeah, again, I mean, we are not going to get into that, but I mean, I have this stuff written in the slides, but this requires a lot more explanation. For example, the nearest neighbor rule, no matter the distribution of x and y, you can show that the Bayes error, right, is less than or equal to the limit of the design error, expected value of the design error, and this is less than or equal to 2 times the Bayes error, right? So you can show from here that this quantity is less than or equal to the uh, to the Bayes error in the limit, right? So in the limit it'll approach the Bayes error, okay, because that's the best possible that you can do, right? So hence the asymptotic expected cost of design is small if the Bayes error is small. However, this result doesn't give you consistency, right? Because it's not telling you that it's going to go to 0, right? More generally, for the k nearest neighbor rule, where k is odd, where the k points closest to x are selected and the class label is defined to be 0 or 1 according to whatever is the majority among the labels of those points. So if k equals 1, you get back the nearest neighbor rule, right? And then you can have the 3 nearest neighbor, 5 nearest neighbor, and so on. Okay. And here the limit of the expected value of epsilon n as n goes to infinity, it can be expressed analytically and various upper bounds exist. All right. And again, I mean, you'd have to take that course or read some papers. In particular, one of the upper bounds is this one, right? And this again doesn't give you consistency because this is not telling you that this is going to go to 0 as n goes to infinity, right? But it shows that the design cost gets arbitrarily small for sufficiently large k, right? That means provided you are taking enough number of you're taking enough number of neighbors, and that's the point that you're making because it's a k nearest neighbor rule, right? Maybe that's what you have seen in your 649 class. Okay, so here I'm just giving the results, and again, you don't need to sweat it out over these things, okay? Because we have too many other things going on in this course, right? We need the big picture, right? But you should at least know what's going on here, right? So the k nearest neighbor rule is universally consistent if k goes to infinity. That means if the number of neighbors that you're taking is going to infinity and the ratio of k over n goes to 0. That means the number of samples increases faster than the number of neighbors. Right? Now, if you're using a classification rule, all right, see, you might go and use a particular sample to learn the classification rule, right? The real test is how does it do on new samples that it has not seen before, right? And if you are designing based on small samples, there is a possibility that your classification rule, right, it might overfit the current data, right, the existing data, to the point that it does poorly on any new samples that you give from the same feature label distribution, right? So that's a problem, right? So a classification rule can yield a classifier which makes very few or no errors on the sample data on which it is designed, but it performs poorly on the distribution as a whole, and therefore on new data to which it is applied. And this situation will be made more complicated by using a complex classifier, because a complex classifier will have a tendency to overfit the data. And I'll give you an example in a few minutes, and if you have small samples. And if the sample size is dictated by experimental conditions, and which it is very much in our case, right? Because we are looking at microarrays, it costs money to do biological experiments, right? They're not going to generate tons of data so that you have statistical significance, right? So so we have experimental constraints such as the cost of or the availability of patient RNA for expression microarrays. Then you really have then the only thing that you have control over is the complexity of a classifier, because you cannot go in there with a complex classifier and tell them give me tons of samples. Right? It's not going to work, right? So you have a limited number of samples, so you should not have come up with a very complex classifier. Try to use a simpler one. Again, think of the same example. If you have a linear classifier, let's say in two-dimensional space, all right, you just need two parameters, all right? You don't need too many samples, right, to learn two parameters. Okay, so you can do a lot better. So the situation that with which we are concerned with is typically referred to as overfitting. The basic point is that a classification rule should not cut up the feature space in a manner too complex for the amount of sample data that is available. Right? If you have a small amount of data, you are going to overfit. You don't want to do that. Right? And the problem is not necessarily mitigated by applying an error estimation rule to the design classifier to see if it actually performs well. Because when you have a small amount of data, even the error estimation is also going to be imprecise. Right? Because everything involves asymptotic results. When the samples are large, then everything is precise. Those are the kind of results that you have. Right? So hence a low error estimate is not sufficient to fully overcome our expectation of a large design error when using a complex classifier with a small data set. And I'll give you an example, right? See here, right, in this example, we have two equal variance circular Gaussian class conditional distributions, right? So we are getting the samples from two Gaussian distributions that have the same variance, but that have different means, all right? Now, if you know that it's a Gaussian distribution, right, you can apply that Bayes procedure, right, and you can come up with the optimal classifier, right. And in this case, the optimal classifier is actually going to be a straight line, okay, separating them. You can do the math, right? I did all that eta x less than half and so on. You can do the math, and I believe one of the homework problems will make you go through that. Okay, so you can do the math. You can come up with the Bayes classifier. So in this particular case, all right, so this boundary is the Bayes classifier, right? This boundary here is the Bayes classifier, right? It's a linear classifier, right, that is separating the two classes, right? But now so you try to learn, so you have this probability, these Gaussian probability distributions, all right? You use them to generate the data, okay? And because you already started with the knowledge of the probability distribution, you can go ahead and theoretically calculate the Bayes classifier, right, which will be these lines, all right, these lines here, right? And now, because you know those distributions, all right, you can use them to generate samples, right? So the samples coming from one of them, you will, label them using circles. The other one with the crosses, right? Right. So there are two different kinds of samples, right? So now, in the two upper figures, all right, you are trying to learn a classifier, right, using only 30 samples, right? And you're doing, I believe it is the 3 nearest neighbor rule classification, right? So you're trying to assign class labels, right, using the 3 nearest neighbor rule. So if you work with those 30 sample points that are given to you, in one case you come up with this decision boundary, right, between the two classes. Another case you come up with this one. So see, it's completely changed, right, because of the small sample size. On the other hand, if you do the same classification with 90 samples that are obtained from these two different classes, then the decision boundary that you come up with is this, right? So notice that, number one, with larger samples, you are much closer to the actual decision boundary, right? Number two, and the decision boundary also is more robust, because when you went from one set of 90 points to the other one, things didn't change too much, right? Whereas in the other case, when you had only 30 samples, this was overfitting the data, right? Because now once you went from this set of 30 samples to the other one, it's completely changed. Okay, that's what you will typically observe. So, if you have a complex classifier, right, with small samples, that's not a good idea. Okay. So note the greater overfitting of the data for the 30-point samples, in particular the greater difference in the two 30-point design classifiers as compared to the difference between the two 90-point classifiers, and the closer the latter are to the Bayes classifier given by the vertical line. All right, any questions? So based on our preceding discussion, right, we come to the conclusion that if you have small samples, right, you're better off doing a constrained classifier design, right? Put some constraints on the classifier so that it has fewer parameters, fewer variables, so that you can learn it from a lot less data, right? So to mitigate overfitting, we need to use constraint classification rules. Now, constraining classifier design means restricting the functions from which a classifier can be chosen to a class script C, right? This leads to trying to find an optimal constraint classifier, psi sub C, right? Belonging to the class of constraint classifiers, which will have minimal error, epsilon sub C. Now this epsilon sub C will be, in general, be greater than epsilon sub D, right? Unless the base classifier happens to lie in that particular class, right? So the cost of constraint, so because you put in a constraint, right, the best possible classifier that you can design, right, is now going to have an error that is higher than the base classifier, than that of the base classifier, right? And so that cost of constraint, this approximation delta C, is epsilon C minus epsilon D, where epsilon C is the error of the best constraint classifier, okay? And so without going through all of this text, okay, I think I can go to that picture and show you what is going to happen, right? So see, so this is the sample size, right? This is the size of the sample. Epsilon D is the error of the base classifier, right? That's the error that you get if you have the probability density, the probability distribution. You design the base classifier, this is the error that you get. That doesn't depend on the sample size, right? Assuming that the right probabilities have been given to you. Now, if you put in some constraint, all right, on the structure of the classifier, you have increased the possible minimum to epsilon sub D. That is the minimal error of the constraint classifier, and that in general will be at least as large as the base error, because the base error is the minimal error, right, without any constraints. So if you put constraints, you will do worse than that, right? Now the next thing is that because you are not given all these probability distributions, right, or the densities, right, so you have to design classifiers based on data, okay? So now you'll have this situation. So you will have the error of the design classifier, which will depend on the sample of size n, right? And now you're going to look at expectation, because if you don't put the expectation, it's a random variable, so I cannot plot it here. So this error you expect, right, if you have a good rule, good classification rule, right, you expect that as n becomes larger, this error goes down, right? And in the limit, it will approach the base error, right? So if for the classifier without any constraints, right? On the other hand, if you're designing a classifier with constraints, right? So first you put in the constraints, you messed yourself up some because you went from epsilon D to epsilon C. But now you have, even this guy, you have to actually design, right? So, and let's say you're designing based on n samples, then you look at the expected error. That also you expect it to decrease, and in the limit you expect it to approach epsilon sub C. Okay. So now, if you're operating with very large samples, right, you're better off keeping the constraint, because if you look in this region to the right of this point, all right, the error of the designed unconstrained classifier, right, expected error is less than the error of the uh, design constraint classifier. So you will go the unconstrained route. But we are going to be operating somewhere in this region, because with microarrays and all that, right, and typically in most of the biological setups, we'll operate in this region. So here the error of the constraint classifier, constraint design classifier, is less than the expected error of the unconstrained design classifier. So therefore, we are better off putting the constraints, right? So that's all that, all this discussion here is talking about, right? And it's, writing the mathematical equations. So if you have the appetite for that, go through it. There's nothing wrong here, but I thought that a picture is much better to explain with a picture, right? Than trying to go through all this. It's not heavy duty math or anything like that, but, you're writing down all these expressions and all that, it kind of, obscures the message. Yeah, so here if you see, that there is an n0, there is a crossover point between the two of them, right? And the net conclusion is that if the number of samples is less than n0, then the advantage of the constraint is the difference between the decreasing solid lines, all right? And the point n0 at which the decreasing lines cross is the cutoff. For n greater than n0, the constraint is detrimental. For n less than n0, it is beneficial. That's what I tried to explain, right? Okay, any questions? So for us, because we are working in the small sample range, all right, we should look at constraint classifier design. So let's look at some standard constraint classifier design procedures, all right. So we are first going to look at the quadratic discriminant analysis, right? So we'll do quadratic discriminant analysis, linear discriminant analysis, then we'll talk about support vector machines and so on, okay? And again, these are quite standard. If you take the course on pattern recognition, I don't know whether he covers these or not. He does, right? Yeah, I mean, these you'll find in textbooks also in pattern recognition. These are not research items, all right? They're already figured out. So a classical example of constraint classification rule is what is called the QDA, or quadratic discriminant analysis. So to discuss that rule, let R sub k, right, denote the region in d-dimensional feature space where the base classifier has the value k, right, for k equal to 0, 1. Again, we are looking at binary classification. There are two classes with class labels 0 and 1, right? So the set of all the values x, right, in that region, right, for which I will spit out the class, the base classifier will spit out the class label 0, right, I will call that R0. The set of all the values of x for which the base classifier will spit out the class label 1, I will call that R1, right? Now, so as we have seen earlier, x is going to be in the region Rk if the joint density of x, right, and y evaluated at k, right, is greater than or equal to the joint density of x and y evaluated at x and j. It's the same thing about that eta of x. Remember, we had eta of x, which was the probability that y equal to 1 conditioned on x. You multiply that by the density of x, you get the joint density that y equal to 1 and capital X equal to x. Right? It's exactly the same thing, right? What I showed you in the derivation of the Bayes rule. So x is in Rk if this quantity, right, the joint density with k, with class label k, is higher than the joint density with class label j, right? That's what we saw over there. Eta x greater than or equal to 1 minus eta of x, right? Because that fx of x that was multiplying eta of x, that's the same in both the cases, right? So it doesn't make any difference. So since f of x and k, since the joint density of x and k can be written as f of x conditioned on the class k times the prior probability of k, right? Once you take the log, so you need to compare these two quantities, right? This is equivalent to x belonging to Rk if dk of x is greater than or equal to dj of x, where the d is for discriminant. The discriminant function dk of x is defined by log of f of x conditioned on k, right? See the product of these two guys. So log of f of x and k, right, is going to be log of f of x conditioned on k plus log of f of k, right? This is going to be the discriminant. This is called the discriminant because for each of these classes, all right, you can compute that, okay? And depending on which one is larger, you will decide whether it's in one class or the other. Right? So now to derive the quadratic discriminant analysis, up to here we have not made any assumptions about the distribution, right? So if the conditional densities f of x conditioned on class 0, f of x conditioned on class 1, these are normally distributed, then this is what and it's a multivariate normal, all right? Multivariate Gaussian, then this is what the density function will look like. F of x conditioned on k will be 1 over square root of 2 pi to the power of n over 2, square root of 2 pi to the power of n, the determinant of the covariance function, right? And then e to the power of minus 1 half x minus the mean of that particular class, inverse of the covariance matrix x minus the mean of that class. This is the formula for the density function of a multivariate Gaussian, right? Pardon me?
I was going to say it's the same as the regular one-dimensional norm. It just is in multi-dimensional.
Yeah. Yeah, the one-dimensional one, you know that 1 over sigma square root of 2 pi, whatever, e to the power of minus x minus mu square over 2 sigma square, right? This is similar except that here now you have a covariance matrix, all right? You just don't have a variance, right? So you should have seen that somewhere, or hopefully if you didn't, go and start, studying that stuff or take a course on stochastic processes, right? And I think we have pretty good courses on that in our department, right? So here KK is the covariance matrix and UK is the mean vector, right? Any questions so far? So now, see, I have the form, so I can plug these guys in here, right? I mean, I have the formula for the class conditional densities. I can plug them in here, right? And then I can compare these two discriminants, right? So if you calculate the discriminant, you get this expression. dk of x is minus x minus uk, because you have an exponential, and then you're taking the natural log, right? Yeah, I guess here we are saying log, but it's really the natural log, right? So the exponent is going to disappear, and you're going to have this expression, right? For the kth class, dk of x is this, right? Now from this so you're going to compare dk of x, all right, with, let's say, dj of x, all right? So you can see that the highest power of x is 2, right? I mean, it's a quadratic in x, all right, on the left, with a quadratic in x on the right, right? So the decision boundary is going to be quadratic, right? Because that x transpose, whatever, kk inverse x term will survive on both sides, okay? So the decision boundary is, so the form of the equation shows that the decision boundary dk of x equals dj of x is going to be quadratic. And that's where this classification algorithm gets its name, right? Quadratic discriminant analysis, right? Any questions on this? Now, if both the conditional densities possess the same covariance matrix K, right, then it's not going to be quadratic anymore. Because if you look at the discriminant on each side, so Kk equals Kj, right? So the x transpose Kk inverse x, right, and then the x transpose Kj inverse x terms on both sides will cancel out. So it's going to become a linear decision boundary. Actually, it'll be affine, okay, because you will have this variable here, right? Okay, so if both conditional densities possess the same covariance matrix K, then log of determinant Kk can be dropped from dk of x, and dk of x becomes this, right, which is a linear function of x and produces hyperplane decision boundaries. Well, not quite. This is not a linear function because it's still quadratic, right? It's only when you compare dk and dj, that's when the linearity will come, because the quadratic terms are the same on both sides. Right? So if in addition we assume that the classes possess equal prior probabilities fk, then these fk terms also can be dropped, right? And we will have a linear decision boundary. Right? And this discriminant characterizes what is called LDA, or linear discriminant analysis, right? So here the classifier is linear, right? It's a classifier that has got a structure, and the classifier will be of this form. Like the class label that it's going to spit out, right, is going to compute a linear combination of all those feature vectors, all right, an affine combination, and then depending on this value, if this value is 0, it will spit out something. If it is different from 0, if it is more than 0, it will spit out one class label. If it's less than 0, it will spit out the other. So where x is x1, x2 up to xd, these are the d features, and t thresholds at 0 and yields -1 or 1, which are the two class labels, all right. So it divides the space into two half spaces determined by the hyperplane that is defined by the parameters a0 through at. So if you set this equal to 0, that's the hyperplane. That's the plane that is separating the two classes. All right. Now the equations for quadratic and linear discriminant analysis, they are derived under the Gaussian assumption. Right? We assume that the class conditional densities are Gaussian, but in practice these algorithms, they perform quite well as long as the class conditional densities are approximately Gaussian. So you derive that, and after that you'll apply it probably to non-Gaussian situations, and in most cases, if it's not too far away from Gaussian, you'll do quite well, right, with the classification. Any questions? Now, owing to the greater number of parameters that have to be estimated for the quadratic discriminant analysis as opposed to the linear discriminant analysis, one can proceed with smaller samples in the case of LDA as compared to QDA. Right? Another point to note is although QDA and LDA are derived under certain assumptions, they are often applied in situations where the assumptions are violated in order to achieve parametric, quadratic, or linear classifiers, in order to get simpler classifiers. Right? Because remember, I said if you have some structure, life becomes a lot simpler. Right? So in such circumstances, their performance depends on the actual feature label distribution and also the sample size. LDA, it's a simpler classifier, so it appears to be more robust relative to the underlying assumptions than QDA. Right? Because QDA has got more parameters, you have to learn more stuff. All right, any questions on LDA or QDA? Next, we are going to move on to a discussion of what are called support vector machines, all right, SVM, right? A popular classification rule to construct linear classifiers is what is called the support vector machine, right? So let's look at the figure, right? So here you have a figure, right, with a bunch of points. There are two types of points, right? You have these circles and then you have the dots, right? You want to find a classifier that is going to separate both of them, right? So before you can use support vector machines, all right, the two classes have to be linearly separable. You have to be able to separate them using a straight line, okay, or a hyperplane. So now, so if you look at these two classes, all right, this is what is called, this line in the middle, it is called the maximum margin hyperplane, right? And these vectors, this is called a support vector, right? This is the vector in this class that is closest to the maximum margin hyperplane. That's one support vector. This one is another support vector, right? From the two different classes, you get the two support vectors, all right? And then you want to basically put in a line in between that is equidistant from the two support vectors, right? So that is the maximum margin hyperplane. And you can mathematically, solve an optimization problem to come up with this maximum margin hyperplane, right? And so if these two classes are linearly separable, you can use a support vector machine to separate. So these are the support vectors, all right? And in between them you have the maximum margin hyperplane, right? To separate out these two classes. So let's go through the text now that I explained the stuff to you in the figure, right? So a popular classification rule to construct linear classifiers is what is called the support vector machine. The figure that I showed you shows linearly separable data set and it shows three hyperplanes, right? The outer lines pass through points in the sample data and the third, which is called the maximal margin hyperplane, is equidistant between the two outer lines, right? And it has the property that the distance from it to the nearest one label vector is equal to the distance from it to the nearest minus one label vector. Like we have a circle and we have dots, one of them we are labeling 1, one of them -1, right? So the vectors closest to it are called the support vectors, right? So the vectors that are closest to the maximal margin hyperplane, they are called the support vectors. And the distance from the maximum margin hyperplane to any support vector is called the margin, right? And the matter is formalized by recognizing that differently labeled sets are separable by the hyperplane. See, the equation of a plane is like ax plus by plus cz plus d equals 0, right? So you can write it something like this. The inner product of two vectors, like ax plus by plus cz, it can be written, right? So the inner product of two vectors equals c, right? Where u is a unit vector and c is some constant, right? So if u inner product with xk is greater than c for all xk that correspond to the class label 1, right? And u times xk less than c for yk equal to -1, right? Then all these points that correspond to one class or the other, all right, will lie on different sides of that hyperplane. So the hyperplane can separate them, right? So that's the idea, okay? Because see this hyperplane here, right? It can separate those two classes because if you write down the equation for this hyperplane, it is basically some inner product, right? Right? Equal to a constant, right? Because this is affine, it's not going to be 0, it's going to be some constant, right? And for vectors here, it will be greater than that constant, and for vectors here, it will be less than that constant, right? So that's how you go about finding that hyperplane, right? So differently labeled sets are separable by the hyperplane u times x equals c, where u is a unit vector and c is a constant if u times xk greater than c for yk equal to 1, and u times xk is less than c for yk equal to -1, right? So now what you want to do is you want to find out the smallest value here, okay? That is going to work, right? U times xk is greater than c. If I make sure that the smallest of these guys is greater than c, then I'm done, right? Same way here, u times xk is less than c. The largest of these guys should be less than c, right? And then I'm done. So the problem becomes the following. So for any unit vector u, the margin is defined to be rho u will be 1/2 because it's 1/2 of that distance, right? I mean, the margin is 1/2 of this complete distance, right? So the 1/2 will be there, and then I will take the minimum of this inner product of u with xk for all xk such that the class label is 1, okay, minus the maximum of u dot product with xk where the class label is minus 1. All right? And that gives me the margin. And the maximum margin hyperplane, which is unique, can be found by solving the following quadratic optimization problem. And I'm not going to worry about this, but intuitively you get what you're trying to do, right? Here this is being formalized, right? As a mathematical optimization problem or a linear programming problem, right? Where you're going to try to find this constant b, and then you will get the vector v of minimum norm, right? So among the set of all vectors v for which there exists a constant b such that this relationship holds if yk equal to 1 and this is less than or equal to minus 1 if yk equal to minus 1, find the vector of minimum norm v, right? And if v0 satisfies this optimization problem, then the vector defining the maximum margin hyperplane and the margin are given by these expressions here, right? And again, if you take a course on pattern recognition, they'll probably go through that. Maybe this will be a homework exercise, right? I don't know. Now, if the sample is, so you can use a support vector machine if the sample can be separated using something like a line, like a hyperplane, right? If the sample is not linearly separable, then you have one of two choices. You could try to find a linear classifier, right, to do an approximate job, or you can find a nonlinear classifier, right? So in the first case, the preceding method can be modified. And a second approach is you map these points which are not linearly separable, you map them into a higher dimensional space, right? Where the image becomes linearly separable, right? And then you construct a linear classifier, and then you map back to the lower dimensional space. All right, any questions? Now I want to give you a classification example, right, from the literature, right, based on microarray data, right? So if you're looking at breast cancers, all right, there are genes that have been implicated in breast cancer, right, and they are called BRCA1 and BRCA2, right? So if a woman carries a mutation in the BRCA1 gene, right, they would be predisposed to getting hereditary breast cancers, right, BRCA1 or BRCA2 gene, right? And of course, breast cancers also arise sporadically where somebody doesn't have those mutations but still they get breast cancer, right? So the key question in this particular study was, can you go ahead, based on microarray data, right? Can you go ahead and classify based on the, breast cancer samples that are given to you, whether it is BRCA1 mutant, right? Or it is BRCA2 mutant and sporadic. I think BRCA2 and sporadic was put in one group, right? So how do you design a classifier, right? And this is a study that was done several years ago, right? I think there were like something like 265 patients or something like that, right? And the classifier that they came up with looks like this, right? So these circles are BRCA1, all right, breast cancer 1, and these squares are breast cancer 2 and sporadic, right? So can you classify those? Well, I mean, there is a decision boundary that you can, that's it, using just two features, all right? This gene and this gene, right? They were able to find a linear decision boundary, right? Separating out these two classes, right? Now, how do you, remember on the microarray you have thousands of genes, okay? How do you pick up these guys, okay? How would you know which two genes to use, two or three genes to use to do this classification? That's an open problem, right? But here, and not only that, I mean, here maybe what they did is they took those samples, they knew the labels, right? I mean, so they knew the class labels. So based on that, they came up with this decision boundary. Now the question is, if you see a new breast cancer case, all right, is this classifier going to work, right? That's a good question, right? If it doesn't work, then it's not that good, right? What is the percentage of mistakes that it'll make, right? I don't know whether in this paper they actually worked on that or not. They might have done what is called resubstitution, right? Which means the same sample that you use for designing the classifier, you test the errors on that, right? Guess what? If you do that, it's going to be a pretty optimistic scenario, right? So there are problems associated with all of this stuff, right? So So we illustrate some results based on regularized linear classification in the case of breast tumors from patients that carry mutations in the predisposing genes BRCA1 or BRCA2, or from patients not expected to carry a hereditary predisposing mutation. Pathological and genetic differences appear to imply different but overlapping functions for BRCA1 and BRCA2. And in an early study, right, that means in the 90s, okay, early in the 90s, involving expression-based classification, CD8A microarrays are used to show the feasibility of using differences in global gene expression profiles to separate BRCA1 and BRCA2 mutation-positive breast cancers, right, and that's the picture that I showed you. So using data from that study, the analytic noise injection method has been applied to derive a linear classifier to discriminate BRCA1 tumors from BRCA2 and sporadic tumors. And the figure shows the design classifier based on two genes, KRT8 and DRPLA, along with its relation to the sample data pairs for these two genes. What can be inferred from this separation relative to population classification between the tumor classes depends on the method that is used to select the features KRT8 and DRPLA, the classification rule to construct the separating line, right? How did you come up? Is this support vector machine? Is it LDA, right, or whatever? And the relationship between the estimated error based on the sample data and the true classifier error relative to the feature label distribution, right? So these are important questions because it's not, I mean, if my classifier performs well on the sample data that I use to design the classifier, that's not of much use, right? I want to see how it is going to perform out in the general population, right? All right, so in that picture, right, we showed you that there were two features that were selected, right? I mean, out of 10,000, I don't know how many genes there were on the microarray, but out of thousands of genes, they selected those two. How do you select the features, okay? How do you select the d-dimensional feature vector that you're going to use to get a good classifier? Ideally, the minimum number of features you have, right, the happier you'd be, right? Because you don't want to use 10,000 genes to do class, and that is still an open problem, right? It's a difficult problem, it's still an open problem, right? Yeah. It is an open problem. There is no good method. I'm going to give you some methods that are used, but these methods mostly use heuristics, right? That's how it is done. And in fact, somebody has shown that you cannot, right? Like if you're looking at D features, right? There is no way for you to go and pick up the best D features, right? From the set of all the possible features, right? Unless you have distributional knowledge, right? So if you don't make any distributional assumptions, you have to test all the combinations. Okay, let's say there are n possible features. Right? Let's say there are 10,000 genes on the microarray, and you're going to choose two of them. Right? So you need a feature set of size 2. You have to check out all the 10,000, choose two possible combinations. Right? You have to do an exhaustive search to figure out which one is going to be the best set of features. Okay, somebody has proven a result like that. Right? All right, so now let's move on to feature selection. Right? Now, if you're looking at the Bayes error, right, the Bayes error is monotone, right, because see, if you're looking at the Bayes error, if you increase the size of the feature set, like if you had, like, let's say 10 features, you make it 12, the Bayes error will only decrease, right? But this is not true about the error of the design classifier that you'll get, because the Bayes error is one thing, okay? It is something that is out there that you really cannot get a handle on, right? Because you don't have the probability distribution. So really the thing that you have to live with is the design error, right? And for the design error, it is not true that if you just keep on adding more features, right, you're going to be doing better, right? So if you add more features, initially the error goes down, the design error goes down, but as you keep on increasing the features, the design error goes up. Right? So the Bayes error is monotone, meaning that if A and B are feature sets for which A is contained in B, then the Bayes error corresponding to the set B is less than or equal to the Bayes error corresponding to the set A. So thus, relative to the Bayes error, if one has a large set of potential features, it is statistically safe to use all of the features when forming a classifier. Right? However, if epsilon an and epsilon bn are the corresponding errors resulting from the design classifiers, right, means from the samples, so on a sample of size n, then it cannot be asserted that the expected value of the classifier that is obtained from a larger feature set is going to be less than or equal to the expected error of the classifier designed from the smaller feature set. Right? So monotonicity does not apply to the expected errors of design classifiers, and it is in fact commonplace for the expected error to decrease and then increase for increasingly large feature sets. And this is called the peaking phenomenon, and this diagram illustrates that. So here is the number of feature variables, all right, D, all right. So, and this is the error. Again, remember the classification error is the probability of misclassification, right? So it can only be a number between 0 and 1, right? If somebody tells you your classification error is 0.999, then your classifier is no good, okay? So now, here if you're looking at the Bayes classifier on D variables, you can see that the error of the Bayes classifier keeps on decreasing, right? If you're using a larger number of features, the error of the best possible classifier is decreasing. On the other hand, if you're using a design classifier, right, with D variables, this error initially goes down, right, as you're putting in more variables. But after some time, probably the information is redundant, right? And with additional variables, you'll probably have more parameters to estimate, right? And the error will actually go up. So one might hope that there is some way of avoiding checking all possible feature sets to find the best one, right? But unfortunately, a classical result states that to be assured of finding the optimal k-element feature set from among n features, one must check all k-element feature sets or all subsets. So n choose k cases, all right? Unless one has some mitigating prior distributional knowledge, which is generally not the case in practical situations, right? And a further problem is that even if one were able to check all the feature sets, how are you going to compare the goodness of the feature sets, right? By doing error estimation. You want to see what is the probability of misclassification based on those feature sets, right? You have a need for error estimation, and even that is pretty poor, right? If you have small samples, right? So the need for error estimation can greatly impact finding the best one. Right? If you're not able to accurately estimate the error, right, then you're not going to get the best feature set anyway. So what do, right? So the best thing to do is, since the optimal feature set is so hard to get, right? You have to go through all those exhaustive cases, then you have to look at, you have to try to do accurate error estimation, and we cannot do that, okay? So the best way is to do suboptimal feature selection, right? So the most obvious approach, so that's why I said it's basically heuristics. When you're doing things suboptimally, it's again heuristics, right? So the most obvious approach to suboptimal feature selection is to consider each feature by itself, right? One at a time, and then choose the K features that perform individually the best. Right? Not a good strategy, right? Because these features might, in combination, they might perform differently, right? So while easy, this method is subject to choosing a feature set with a large number of redundant features, thereby obtaining a feature set that is much worse than the optimal, right? Not only that, features that perform poorly individually might do well in combination with other features. Think about AND gates, right? Inputs to AND gates, right? In combination, things work, okay, but individually it's very poor. So a common approach to suboptimal feature selection is what is called the sequential selection, either forward or backward, and their variants. So in sequential forward selection, you start with a small set of features, perhaps one, and you iteratively build the feature set. So when there are, so at the kth stage, when there are k features, x1 through xk in the growing feature set, all feature sets of the form x1 through xk and then one more feature, w, are compared, and the best one is chosen to form the feature set of size k plus 1. Right? The problem with this is that you just keep on adding, right? So if one of these guys, let's say x2, is not needed anymore, you don't have the ability to throw that out, right? So you will do, what we now want to do is to add and then also be able to subtract, right? Again, it's all intuitive heuristic stuff, right? But it works, and that is the state of the art, right? So a problem with sequential forward search is that there is no way to delete a feature adjoined early in the iteration that may not perform as well in combination with the other features. So the sequential forward search look-back algorithm, right, aims to mitigate this problem by allowing a deletion. For it, when you have k features, all right, you're going to append two more features to it, right? And then, so all feature sets of the form x1, x2 up to xk and wz are compared, and then the best one is chosen, right? And then you will delete one of the features, right, from here. So all k plus 1 element subsets are checked to allow the possibility of one of the earlier chosen features to be deleted, the result being the k plus 1 features that will form the basis for the next stage of the algorithm, right? So you're adding features and also you're allowed to drop features. All right. Now flexibility can be added by considering sequential forward floating selection. Right. So again, you could let the number of features added float. Right. Where the number of features to be adjoined and deleted is not fixed but is allowed to float. Now when selecting features via an algorithm like sequential forward floating selection that employs error estimation within it, one should expect the choice of error estimation to impact feature selection, right? And the degree depending on the classification rule and also the feature label distribution. In general, feature selection is an important and difficult problem with many proposed algorithms but little theoretical support, right? Mostly heuristics, right? For the most part, comparison of feature selection algorithms is via simulation, in which algorithms are applied to particular feature level distributions. Even if good feature sets exist, for small samples, the likelihood of finding one whose performance is close to optimal may be small. This is due to the difficulty of classifier design and inadequate error estimation. With small samples, you have trouble all over the place. And the problem is exacerbated for counting-based estimators like cross-validation on account of a multitude of ties among feature sets, right? So different feature sets give you the same estimation error or error estimate. Okay, so next we move on to the topic of error estimation. That means figuring out how good your classifier is. Okay, how do you estimate the probability of misclassification? So error estimation is a key aspect of classification. If a classifier psi-n is designed from a random sample Sn, then the error of the classifier relative to a particular sample is given by the expectation of the magnitude of y minus psi-n of x. Because this is the classification error. Okay, class label, right? Predicted class label minus actual class label, right? This is the predicted class label, psi-n x. The classifier is predicting that minus the actual class label. Take the expectation of that, where the expectation is taken relative to the feature label, distribution f. So this is the error corresponding to the sample epsilon n. But again, that is also a random variable, right? So you have to take one more expectation. You have to take the expectation over the joint distribution of the samples Sn, and that is giving you the expected error of the classifier, right? So in practice, the feature label distribution is unknown, right? You don't know this distribution f, right? And the expected error must be estimated, right? So now what do you do? Again, I mean, there are things that you will do that seem to be most obvious or intuitive, right? If you have a lot of sample data, right, you would split up the data into two parts. One would be the training and the test data. So the training data you will use to train and design your classifier, right? And then the error will be the proportion of mistakes that it is making on the test data, right? Now the problem with using both training and test data is that one would like to use all the data from the design, because more data means a better classifier, decreased design cost, right? And this is especially the case with small samples, right? You cannot afford to you cannot afford to put away some of the data for testing purposes later on, because you need as much data as you can get to bring down the design error, right? So one approach, so people have used different approaches. One approach is to use all the sample data to design a classifier and then estimate epsilon n by applying this classifier to the same data, right? And this is called the resubstitution estimate, right? Because the same data is being used to do the design and also to test. And so the resubstitution estimate is the fraction of errors made by the classifier on the sample training data. Resubstitution, you naturally expect that it is going to be biased low because it's very, very optimistic. You're not using new data, right? The data on which you train the classifier, that's the one that's being used to test the classifier, right? And it is, so resubstitution estimate is often severely low bias when samples are small. And as with all error estimators, performance depends on the classification rule. And an extreme case is that the resubstitution estimate is always zero for the nearest neighbor classifier. Right? If you use the nearest neighbor classification rule, you do the resubstitution estimate, right? It's whatever classification you did is 100% accurate, right? So you will get an error is going to be zero. Now, a common way of performing error estimation using the same data on which the classifier designed is to apply what is called a resampling strategy, right? So you might leave out some of the data, right, and use that to do the test, right? So cross-validation is a resampling strategy in which the classifiers are designed from parts of the sample and each is tested on the remaining data and the error estimate is obtained by averaging the errors, right? So if you're doing k-fold cross-validation, you will break up the sample SN into k different folds, okay? So one of the folds you will keep for testing later, all the other k-1s you'll use for designing the classifier, and then see how many mistakes it's making on the, or the proportion of mistakes it is making on that one fold that has been left aside, okay? And in this case, the error estimate is unbiased. Uh, and if you have like n data points, okay, and you do n-fold cross-validation, that means you'll basically leave one point out, right? And that's called leave one out error estimation, right? So while not suffering from severe low bias like resubstitution, cross-validation has, the problem is it has got large variance, right? Which can kill you in small sample settings, and therefore its use is also problematic. Yeah, this slide, let's not worry about the stuff on this, because if you're not familiar with the variance and mean and all this unbiasedness, this is only going to confuse you. So let's just keep moving on. But so we have covered two methods. One is the resubstitution estimate. The other one is cross validation. A special case of that is leave one out cross validation, right? So just keep that in mind. Another method is called the bootstrap method. Again, there you basically sample from the data, right? So bootstrap is a general resampling strategy that can be applied to error estimation. A bootstrap sample consists of n equally likely draws with replacement. So you draw them and then before you draw the next time you replace, right? So you get different samples, right? So from the original sample SN, some points may appear multiple times, whereas others may not appear at all in the sample that you're taking. For the basic bootstrap estimator, the error that you get, right? The estimated error, the classifier is designed on this bootstrap sample and tested on the points left out. And this is done repeatedly, and the bootstrap estimate is the average error made on the left out points, right? And this quantity, the error of the bootstrap estimate tends to be a high bias, I'm sorry, the error estimate obtained using the bootstrap method tends to be a high bias estimator of the actual expectation of the error, since the number of points available for design is on average only 0.632n. And to arrive at this number, you'll have to do some math with the draws and all that stuff, right? And the 0.632 so you're saying that the resubstitution estimate is low biased, it's too optimistic. This one is high biased, right? So it's pessimistic. So the 0.632 bootstrap estimator tries to correct this via weighted combination of the bootstrap estimate and the resubstitution estimate, right? And the weighting is through this factor of 0.632, right? Again, I mean, this is all hand waving, right? Hand waving stuff, heuristics, right? Nothing said in concrete. Okay, now the last topic in the context of error estimation is what is called the bolstered resubstitution estimator, where what you're trying to do, all right, is that, see, if points that lie close to the decision boundary, right, there is a possibility of misclassification over there, right? Like this point, let's say it lies in the correct boundary, right, but it lies in the correct region, right, in the correct class, but it is a lot closer to this boundary, okay? So in order to capture that, okay, what I might say is that instead of using a single point, I'll put in some small, circle or some small ball around that, around each sample point, right? And then I will count this also as a probability of misclassification, right? So you're basically bolstering those sample points, right, by putting circles around them. Again, how big should the radius be and all that? That's a research issue, right? Like you've taken Professor Braganita's class. They worked on this particular method, okay? So in resubstitution, there is no distinction between points near and far from the decision boundary. The bolstered resubstitution estimator is based on the heuristic. Again, based on heuristics, the relative to making an error, more confidence should be attributed to points far from the decision boundary than points near it, right? So this is achieved by placing a distribution, which is called a bolstering kernel at each point and estimating the error by integrating the bolstering kernel for each point over the decision region that the point should not belong to. That's what I showed in that picture, the shaded region, and then summing those integrals rather than simply counting the misclassified points as in resubstitution. And the procedure is illustrated in the figure for a linear classifier. And the key issue is the amount of bolstering, the spread of these bolstering kernels, okay? Yeah. And there is some trade-off over there, okay? And let's not worry about all that stuff, but if you're interested, you can go and, you can look at our book and it'll have references to those papers. But this is just, some other, extra method. This is, and again, I don't think it's even that much mainstream. Like if you look at LDA, QDA, support vector machines, those you'll find in any book, right? This one probably, I mean, it's still at the research stage in research papers and all that, but it is there for anybody that might be interested, right? Okay, so we've finished the chapter on classification. Are there any questions? Otherwise, let's stop here for today.